Well, hi guys, we're going to deal with points of inflection part 2 today, and I hope you'll find it very interesting. It will bring together all of the theory which we dealt with in the last session. So let's get going and have a look. First of all, we've got a typical exam question here. We've got d2y dx squared equals x squared minus x, and dy dx equals 0 at x equals 0. Then the graph will have, and all of that we've got to choose from. Now, let's have a little look. Looks like we're talking about local minimum, local stationary points of inflection, all this kind of stuff. So that's really what we've got to diagnose, where the stationary points of inflection are, and all that kind of stuff. So let's go for it. I think probably the best place for us to start is the beginning, which is d2y dx squared equals x squared minus x. Why don't we set that equal to 0 and use that as our to find the x-coordinates of the points of inflection, and then I suggest we then anti-diff to get dy dx and find out which ones are stationary. Now that'll be a very, very big help, I think. Probably it might just all fall out for us then. So let's go for that. So when d2y dx squared equals 0, if we set that equation there equal to 0, we'll get x is 0 or x is 1. So they would be the POIs, wouldn't they? I think so. Now we're going to anti-diff now, as I was suggesting. And yes, that looks good, doesn't it? Plus the constant of integration c here. Now we better see what c is and put our boundary condition in. We know that dy dx equals 0 when x equals 0, which would tell us that c is 0. Okay, very good. Now, that's where we get to there. And if dy dx equals 0, that's a stationary point, we get that, don't we? If we rearrange it a little bit, and, very interesting. We get that, and therefore we get x is 0 or x is 3 over 2. Okay, so far so good. Now you'll notice that the POIs, they were at 0 and 1, and there's stationary points at 0 and 3 on 2. So therefore it would indicate to us that this point here is a stationary point of inflection, right? This one here is just a point of inflection, and this one here is a stationary point. And that all points to E for you and me. There it is, okay? So it was pretty easy really, but you just got to know what you're doing, okay? Very good, very good. Let's go on. Now in this question here, we've got d2y dx squared equals 12x squared minus 36x plus 24. And we've got dy dx equals 0 when x is 1 and y is 0 when x is 3. They're our boundary conditions. And let's keep going. We've got to find the x-coordinates of 2 POIs and 2 stationary points, showing that one POI is stationary. That's the first thing we've got to find. Then we've got to find whether the stationary point which is not a POI is a local maximum or minimum. Okay, we know how to do that now, remember, from last time. And we've got to find y in terms of x. That'll be from anti-diffing for sure. And then find the coordinates of the stationary points, POIs and axes intercepts. Goodness me, this looks like everything. And then lastly, we've got to sketch y along with its first and second derivative functions on the same set of axes. Well, that is a very comprehensive list of asks, and I think it's a good question because it'll bring it all together and just sort of put it all into a practical working situation where we get a much deeper and more coherent understanding of that theory that we dealt with last time. Okay, let's go with A today. We'll start off with the d2y dx squared equals that, and let's basically find when it equals 0, because that would indicate a POI, wouldn't it? It certainly would. That's going to be very nice because the 12s are all going to cancel through, aren't they? How beautiful. How beautiful. And now we can solve it. Using the null factor law, we can solve it for x, and we get x is 1 and x is 2, right? Now, it's very necessary, guys, if you really want to test for whether you've got a POI, you have to test the sign of the second derivative either side of those points. Because at a POI, remember, the second derivative has to change sign from plus to minus or minus to plus through 0 at the POI. So we've really got, if we're going to verify that x1 and x2 are POIs, we've got to do that, right? So let's test. When x is a half, I worked out d2y dx squared was plus 9. That's just to the left of x is 1. When x is 3 over 2, that's between x is 1 and x is 2, we get d2y dx squared is minus 3. Well, that's looking very promising because it's changing from plus to minus through the coordinate x is 1. Okay, now when x is 5 over 2, which is just to the right of x is 2, we get plus 9. Look, this is looking mighty fine. Mighty fine. So if I was to do a little sign diagram for you, I'll illustrate the point. Along here, I've got, this is just x I've got here, and I'm going to do the sine of d2y dx squared plus up here and minus down here. Okay, now, okay, it was plus to the left of x is 1. It was 0 at x is 1, and then it morphed down into minus between 1 and 2. Look at that. It's absolutely perfect. Now it was 0 at 2, and then it morphed up to plus 9 when we had 2.5. So look, it qualifies, guys. It's changing from plus to minus through 0, through being 0 at where x is 1, and then it's going back from minus to plus through 0 at x equals 2. So it's definitely changes sign at 0 points, therefore they're POIs. No problem. So x is 1 and x is 2 are POIs. Okay, that's that bit done. Now, what we've got to do now is find the two stationary points, showing that one of them is stationary. Alright, so let's go. We'll anti-diff now, and we do that. We get dy dx equals that thing plus the constant of integration c as shown. And let's sub in. We're given a boundary condition that dy dx equals 0 when x equals 1, so that was given, and we're going to sub it in. That'll give us c. Blah-de-blah-de-blah. Looks like c is minus 10. Isn't that interesting? Well, it tells us that. That's what we got for dy dx. Now we've got to work out the stationary points. Well, look, we had to prove that one POI is stationary, so that's a pretty good bet that if we put in 1 or 2, we're going to get dy dx is 0. So let's try 1. Ah, look, we've hit the jackpot already. It equals 0. So that where x is 1 is a stationary point. It's also a point of inflection, so therefore it is a stationary point of inflection. Okay? Do you get that? It's definitely a stationary point of inflection. So that's really great, isn't it? So let's go over the page now. So what we have to do now is basically work out the other stationary points, and we'll just keep going. Okay, so we've got dy dx equals that. We've got it equals x minus 1 times some quadratic. Now, I'm using my little alpha technique here because I know that the whole thing has to, well, 4x cubed, right? The leading term has to come from the front terms in these brackets. So that has to be 4x squared. Otherwise, you wouldn't get 4x cubed here. Similarly, this one here has to be plus 10 because plus 10 times minus 1, the trailing terms give you the trailing term here, which gets you to minus 10. So therefore, the only term we don't know is the coefficient here of this x term, which I'm going to call alpha. And by expanding the right-hand side, the x squared term from the right-hand side, this thing with the brackets, right? Just the x squared term, you are going to get, basically you'll get the x here times alpha x will get you a squared term, x squared term, and the minus 1 times the 4x squared will get you an x squared term. So that'll get you that, which gets you alpha minus 4 times x squared, right? Now that has to equal, guys, that has to equal this thing here, this minus 18x squared, doesn't it? So yes, it does. So therefore, equating coefficients, equating coefficients, we get minus 18 equals alpha minus 4, and we can solve it for alpha, which is very neat. Alpha equals minus 14. Now, I don't like polynomial long division much. I find it annoying, takes up too much space, it's tedious, so I just do the alpha technique. So I recommend it to you if you like it. Otherwise, by all means, go with the polynomial long division and have a good time with that. So therefore, I've got this thing scun now, basically. I've taken a 2 out here, because this was 4x squared minus 14x plus 10. Wasn't it? Yeah, it was. So basically, I've taken a 2 out there and I've just factorised it down. Now, all I've got to do now is factorise this and set it equal to 0, and I've got all my stationary points. Oh, that was nice. That factorised very nicely, didn't it? Okay, so therefore, if you put that equal to 0, you, by the null factor law, you get x equals 1 or x equals 5 over 2. They are our stationary points, and we found out that one of them was a stationary point of inflection, because we found our points of inflection on the previous screen, didn't we? This one here is just a common or garden stationary point, nothing wrong with that. Don't want to give him an inferiority complex. So that's that. Now, okay, so from earlier, the POIs occur at x is 1 and x equals 2. So x equals 2 is not a stationary point of inflection as required. It's just a point of inflection, right? So to summarise, we've got x equals 1 is a stationary point of inflection, x equals 5 over 2 is just a stationary point, and x equals 2 is a POI, but it's not a stationary one, okay? Now for part B, we had to work out that whether the stationary point, this one here, which is not a stationary point of inflection, just a stationary point, in other words a local max or min, we had to work out whether it's basically is a max or it is a min. And we're going to use our second derivative, our new wonderful little tool in our tool chest of maths, to work out whether that is a local max or a min by using the second derivative. And if you remember, if it's a local min, the second derivative is going to be positive. If it's a local max, the second derivative is going to be negative. Okay, so let's go for it. We're going to plug in the value of 5 over 2 for me and you. Yes, we knew that. Now, when x equals 5 over 2, here we go. We get this, we get this, we get this, and we get that, and it's going to be positive. So it's a local min, guys. When x is 5 over 2, we've got a local minimum, okay? It's pretty exciting, isn't it? Okay, now we come to part yes, thank you, that's right, and we're going to come to part C now, where we're going to actually solve the whole thing for y and then get the actual x and y coordinates of all these interesting points we've just been discovering. Okay, so the final anti-diff is about to happen. There it is, our dy dx equation. Therefore, anti-diffing that, we get y equals all of that. Now we've got to diagnose what d is, okay? And we were given a boundary condition where y was 0, x was 3. So if we substitute that in, we'll work out what d is in a flash. All of that, blah, and d equals 3. How interesting. So therefore, we've got our y now. We've got our y where we want it, and put a box around him, because that's a major accomplishment. And, okay, so the only thing left for us now to do is for D, part D, was to get the coordinates, the x and y coordinates of all those points, and then to sketch the three graphs, the y, the dy dx, and the dt y dx squared, all on the same set of axes, right? So here we go. Here's D for you and me. When x is 1, y was 0. Oh, when x is 1, if you substitute that in, from into here, you get y as 0. So not only is it a stationary point of inflection, it's actually an x coordinate. How interesting. That's very good. When x was 2, remember that was also a POI but not a stationary one. So that's we get y as minus 1 by substituting into here. Very good. Now, yes, thank you. When x is 5 over 2, that was, now what was that again? That was a local min, wasn't it? Oh yes, we substitute that in and we get all of that. Looks like it's 216 to 32. It's not quite minus 2, it's minus 1.2 something. Yes? Alright, that's what that is, a stationary point, which is a local minimum. And when x was 3 and y was 0, that is basically an x-intercept. And when x is 0, if you substitute x as 0 into all of this stuff, you get y equals plus 3, which is a y-intercept. Okay, so we're ready to go with the graph now. So over the page we go. And now there is our Y graph. How fascinating this is. Let's have a look at him. He's a very nice looking quartic, isn't he? This is our y-intercept where x was 0, y was 3. This is our, look at this lovely looking stationary point of inflection. It's beautiful, isn't it? Yes. And we're coming down to here, which is our other point of inflection, but not a stationary one. Never mind. Better luck next time. And we've got here, this one here is our local minimum. And it looks like it's, yes, minus 1.69 at 5/2. And here is our 3 and 0. That is our other x-intercept, okay? It's beautiful, isn't it? It's really beautiful. So we really diagnosed it very well. Let's have a look at the gradient function now. And we'll see if what we learned in the last video works. This is a stationary point of inflection, just to point out the obvious. This is a POI, but not stationary, right? Now here comes the red graph is the gradient graph. Now, remember that what I said, when you have a point of inflection on the blue graph, the original graph, you have a local min or max, don't you, on the gradient graph. Indeed, that is a local max, and indeed, this is a local min, right, on the gradient graph. Yes? Okay, so that's making sense. That's a local max, that's a local min. All right? Now, here's the second derivative. Here's the gradient of the gradient, if you like. Okay, the second derivative. Now, what did I say in the last video? If you had a point of inflection on the original graph, and you have a local max or min on the gradient graph, then what do you have at a point of inflection? You have 0. The second derivative is 0, and in fact this is 0, and this is 0 at this point, so it makes perfect sense. That's a 0, and that's a 0. Okay, so here comes our beautiful acronym. So if you've got a point of inflection on the original, you're going to have a local max or min on the derivative, and you're going to have a 0 point on the second derivative. Okay, alright, very good. Now we're going to have a look at the same thing all over again now, but we're going to concentrate not starting at the POI for the original graph. We're going to basically concentrate on the maximum or minimum points of the original graph, and then work down the scale to the second derivative again. So over the page, there's our original graph. Now let's point out the stationary points now, the max or min, or actually just the stationary points. That's a stationary point, although it's not a max or min, it still qualifies as a stationary point. This is the other stationary point, right, on the original blue graph, the quartic, okay? Now, let's have a look at our gradient function. There it is. Now, when you have a 0 gradient on the blue function, the original function, the original quartic, if you have 0 gradient, then obviously you have 0 value on the gradient function, and you do have 0 value here, and you do have 0 value there. Okay, that's a 0 and that's a 0, right? Very good. And then what did I say you had on the second derivative, right? Depends on the nature of the stationary point, doesn't it? If you have a stationary point of inflection, there's the graph, the RCB. If you have a stationary point of inflection, any kind of a point of inflection has a 0 point on the second derivative. So that's going to give you a 0. And remember this one now. This one here, the blue graph here has a local minimum. That's the other stationary point on the blue graph. It has a local minimum, right? So if you have a local minimum, what did I say? Yes, you have a plus or a minus, but it's a plus, right? A plus on the second derivative. So there it is. You see, at that point there, which is 2.5, x is 2.5 on the original graph, you have a local minimum. You have therefore you have 0 value on the gradient function, and on the second derivative it's plus. It's right up there. So it works perfectly well. Everything works beautifully. So I hope that's tying it together for you. to sort of consolidate on that theory from the last video. Here comes our acronym. So if you have a max or a min, or indeed just any kind of a stationary point, this one is not a max or a min, but it's still a stationary point, so it still falls within the ambit of this acronym. If you have an m there for the original, you have a 0 for the gradient function, and you also have a plus or a minus for the second derivative. A plus for a local min on the original, a minus for a local max on the original. Okay, I think that's it. Thank you, and go and do some practice. Go forth and do some practice. You'll get really good at it, and you'll be so confident you'll be unbeatable. Okay, and thanks for watching, and we'll see you next time.